So hello again. Tonight we're going to talk about 3D printing quantum effects. You may have heard of 3D printing. You may own a 3D printer, but this is a printer that can print down to billionths of a nanometer, billionths of a meter, nanometers. So we'll get into detail about that. But first, for those people that aren't aware of what a 3D printer is, I've got an overview, a primer, so to speak, on 3D printing. So what we're talking about is new ways that space exploration is fabricating stuff. They're using 3D printing machines specifically designed to make, the cylindrical shapes of rocket propulsion stages, the cryogenic tanks, the engine nozzles. These are all nowadays 3D printed. They print faster and they can embed parts. Something that might be 70 different assembly parts can now be 3D printed as just one part, which makes it stronger, more reliable, faster to assemble, and lighter in weight. So 3D printing is really improved space science by making better rockets. And they found that as, other things in the space program and astronomy could benefit from, fewer fasteners, lighter weight, cheaper, those kind of things, they started using 3D printing for other stuff. The list goes on, but they found in the last 10 years that if you can print really, really, really small stuff, that not only can you be successful at printing really tiny stuff, but also physics behaves differently. Particles become particles, like light. Photons can be negotiated by things you print at the nanoscale. Electrons can be negotiated or maneuvered at the nanoscale. But first, you've got to have a 3D printer that prints that small. These 3D printer things, you may have heard of them, but you think, oh, that's only for like a small audience, and that'll never affect me personally. Like, by the way, did you know that cosmetics already have nanoparticles in them? Because they found that cosmetic fillers, if you really want to fill in issues in the skin or cover them, if you make the material nanoscale, it fills in better, it makes it look thinner. Cosmetics involve nanomaterials. Medical, if you have a pharmaceutical you need to deliver inside of a person, like not just in their throat, not in their stomach, but down into their intestines, if you can put a coating at the nanoscale level onto small clusters of molecules of that pharmaceutical, then it will lodge in the small intestines and deliver the medication more directly. Delivery of pharmaceuticals, gases, those kinds of things are done at the nanoscale nowadays. And if they can make batteries last longer by making the electrodes have a larger surface area due to them being nanoscale metamaterials, now you can have an implanted device like a pacemaker or defibrillator that the battery lasts longer than 3 years, more like 5 years. So that really improves your quality of life. In the industrial sector or the communications sector, they're finding out that quantum effects at the nanoscale level are really improving things. But the focus of this presentation will be, we'll get to the nanoscale stuff and you'll see a lot of stuff in that regard. But first, for those people that are not aware of 3D printing and how that works, we'll do a little bit of treatise on that. So when you're fabricating things, when you're making things, you can do it one of two ways. You can start with that large block of marble, and then you can chip away until you get the statue. So that's called subtractive manufacturing. Or you can start with a clean slate and then add stuff layer by layer until you come out with that 3D printed statue, and that's called additive. And what we're going to focus on is additive down to the nanoscale. And over here on the right, there's 3 different pictures. The one at the top is a computer numeric control drill bit. It's a router bit, and it's routing a channel in a piece of aluminum. That's subtractive. And then the next thing you've got is a lathe, which rotates a piece of material, and then you push the blade against it to remove the material. So on the top one, the material's sitting still, and the router head moves around. The next one down, the material spins, and then you push the carving knife into the material to take off material. And then the one at the bottom is a XYZ 3D printer. The print bed on that one moves back and forth, and then the print head moves up and down and horizontally. That's a very common 3D printer. They're inexpensive nowadays. You can get them for under $300. I wouldn't go with the ones that are under $100. They're just not reliable enough. But one that's under $300 is good, and it's something you can keep in quality and such. So let's start talking about the kinds of 3D printing. There's what is known as fused deposition modeling, or FDM. That's the common 3D printer. And nowadays they're fancy enough that they can print in multiple colors. But what they do is they take plastic material, they heat it up, and then they squeeze it out through a very fine nozzle. And then the nozzle moves around, and the plate that it's on moves around, and it lays out this material that's been heated, and it leaves a little trace pattern, and then it blows air on it to harden it. And then as it does that layer by layer, you get objects. And they can use different kinds of formulations of plastics. They can add different materials to them, carbon fiber, glass, even metal powders, and they can make them matte finish or gloss or shiny or reflective or even conductive nowadays. The bed that the print takes place on can either be cold or heated. If you heat it, you can make taller things because the printed object will actually stick to the print bed. So as it's whipping the filament around, it doesn't break the thing you're printing loose from the print bed. Then there's another kind of printing that's called stereolithographic additive, or SLA. This is where you have a vat of resin, and then you have a UV light source coming up from the bottom, going through an LCD panel, and it actually hardens the lowest layer of resin. And then it will move up further to get the next layer of resin on the bottom. And it does that layer by layer by layer as it draws the 3D object up out of the vat of resin. And you need supports. That's this stuff you see on the left, all these rods. You break those away once you get the 3D print done. But you have to do post-processing. You have to, like, okay, once you get it printed, you have to break it off the print plate, break off the support structures, and then you dip it into a vat of isopropyl alcohol to remove any of the liquid resin that is on the, sort of sticky on the outside. You remove that, and then you put it inside of a chamber with some deep UV lights for a while, and it hardens the outside surface of it. So different ways of 3D printing, making use of all the same technology for micro precision and such, just different mechanics and chemistry. Then the other one that's getting a lot of attention these days is selective laser sintering. This is where you have a container of particles, plastic particles, and you raise it up, and then you smooth off the top surface of it, and then you have a laser that melts the particles in certain areas to make a flat top, and then it puts another layer of particles over that, and then melts more. And it just does this again and again and again and again. And eventually you wind up with this thing called a cake or a brick that's a giant lump of particles that are either fused or not fused. And then you have to break out the object that you've 3D printed from the cake, and then you use an air pressure nozzle to blow off all the loose debris. Think of it as if you did SLS printing of marble, Michelangelo's statue of David, it would come out as a giant block of powdered marble, and then you'd break it all off and blow it off, and there would be the statue at much higher resolution than Michelangelo could have ever thought possible. And then its competitor is from Hewlett-Packard. The guys that make inkjet printers, they took the inkjet printing technology and said, if instead of colored ink, what if we squirted like glue? So they have microfine print heads that spray what is known as a binding agent into the powder, and it glues the layers together. And then afterwards, you still have to break it apart, break the object apart from the cake. And the part is now referred to as a green part. It's kind of like when you make ceramics and you come out with a green object, and then you have to fire it in a kiln. Same sort of thing. You have the particles that are held together with the binding agent, and now you're going to put that in an oven and sinter the particles together to make your object. And then you have to have it cool down. And they're doing it with wire as well. So if you have a hot enough source, you can actually have a wire come out, and either electrically or using lasers, you can actually melt the end of the wire, the tip of the wire, and draw that around like as if it's a 3D printer printing plastic. So you can make really heavy metal things, hard metal things, using direct energy deposition like rocket bodies or cryogenic tanks or rocket nozzles, or GE is actually making jet turbine blades using DED and deposition. Now, the surface is going to be rough, so you have to grind it smooth afterwards. But yeah, even big, heavy things can be made using 3D printing. Now, the reason why there's such a growth in 3D printing is all the stuff that is used to make 3D printers work, all the mechanics, the software, the applications, you can reuse that stuff. So you can switch between different types of printers and come up with new kinds of printers. Just because you've seen FDM printing, take a look at SLS printing, take a look at MGF printing. You can see the parallels in, hey, they just reused this or did that like they did in that. You can scale that down, and now you can come up with things that are very, very small scale or very high resolution that are borrowing from all of that in the last 5 or 10 years history of 3D printing. One thing I found out this week is obviously you can 3D print buildings using cement. There are companies trying to do that. You can 3D print dental implants like the crowns. You can 3D print crowns, which makes them cheaper, so you don't have to send out to a service to make the crowns anymore. If the dentist is savvy enough and spends the money, he can take the image, digitize it, and then 3D print a nice ceramic crown in the office. You can 3D print optical lenses called super lenses. All this is possible just by taking the technology, making it smaller, and then changing the materials. Speaking of the materials, FDM uses various kinds of plastics, and there's a long list of different kinds of plastics, and you can add stuff to it to make it different. You can add stuff to it to make it have different effects. You can make gold colored shiny plastic filament, and it looks like gold because once you heat it up and it cools down, it gets darker. So it looks like you made something out of gold when it's just 3D printed. Plastics, you can get into softer things. I found out there's special kinds of 3D printers that will print elastomers or silicone. Yes, there are 3D printers making silicone breast implants. There are 3D printers making grippers, stuff like that. There are liquid resin polymer printers. They use UV, but they can now add ceramics to that, and that's how you get your dental implants. Obviously, the metal ones you can do with direct deposition. So how do you get access to these fanciful 3D printing devices? Well, if you want to spend the money and you're really deep into it, you can actually buy an FDM 3D printer or an SLS. If you're going to get started, I'd say FDM. SLS, there's a lot of stinky, goopy things that you have to wear a mask for and wear gloves, and it's a lot more difficult. FDM's a lot easier. But the more expensive ones that you probably would look at, I'll create the model, but then I'm going to pay some service provider to print it out for me, and then they'll mail it back to me. The MJF or the metal ones, you probably want to do it that way. But so long as there is a demand for these things, the capability will come down to lower price levels, and the resolution and accuracy will get you finer and finer levels. So how else is this affecting us, in our day-to-day lives? And what you find is that prototype or limited production parts are being made using 3D printing today. Food products, I've seen 3D printing of chocolate and cookies, and you can put little insignias on your chocolate layers and your cookie. 3D printing jewelry, that's something that's done nowadays. Obviously, ceramic dental crowns and your dental periodontal alignment mouthpieces, rocket nozzles, aircraft engine parts. But this is all before you get down into the nanoscale. But they're going to get there because it's just too profitable for them not to. Okay, here's the first example of tiny. This castle was 3D printed at the micron scale. Now, a micron is a millionth of a meter, not to the billionth, but to a millionth of a meter. This entire castle is about 4/10 of a millimeter by width, by depth, by height. That's tiny. That's fraction of a millimeter. That's less than half a millimeter in size, is the entire castle. Not a layer up, the entire castle. The smallest features are about 10 microns or 10 millionths of a meter. And the only way they could actually see this in detail is using an electron microscope. So that's the first level of tiny. And we're not even at nano yet. By the way, if you really want to watch this thing being printed in real time, there's actually a video at the end that I have a link to where you can see it. But how small is small? So when you get down to the nano level, quantum physics effects start to take place that aren't present at larger levels. So once you get down smaller and smaller and smaller, there are things you can do, like putting up walls or channels or drilling holes, that if you did that on larger scales, it wouldn't affect anything because you'd be above light wavelengths and all light would go through, white light would go through. But when you drill it small enough or you put a block up small enough, you start to affect specific things. Like if you make it around the 8 to 10 micron level, 8 to 10 millionths of a meter level, you can now steer human blood cells. So you can direct the flow of blood cells without actually affecting the blood cells themselves. They won't coagulate or dry up. They'll just flow in channels. You can see on the left the sizes, the diameter of a human hair. You get down to wavelengths of light. You get down to sub-nanometer, where you're talking about picometers, the diameter of a water molecule. Well, how small is small? You get down to femtometers, or billions of meters, and now you're the size of protons and neutrons. As they get smaller and smaller, we get new scale factors. There's a couple of new scale factors down below femtometers. Once you get down to that level of surface smoothness, you can now start to print distortion-free lenses, filters, and diagonal mirrors. So you get better reflectivity and better image capture. Here's an example of nanoscale in the commercial products that are out there today. Quantum dots. So if you make particles small enough that only certain wavelengths of light will be affected, will phosphoresce, you can actually have the diameter of the material dictate what color light it will produce. So if you're down at the 2 to 3 nanometer level for your quantum dots, and you can see these are vials of quantum dots, and they shine a UV light through the back of it, and out comes 2 to 3 nanometers, you get blue. You enlarge that up to 5 to 6 nanometers, which is not a lot of difference, and you get red. Green, I guess that would be 4 nanometers, somewhere in the middle. But those are in quantum dot TVs that you go buy at your local Walmart today. So quantum level things are in your life today. Maybe not your personal life, but certainly in the market. Here's an example of quantum effects. TV antennas. You've probably seen one of these sort of different length rod antennas. They call them Yagis. They're useful for picking up TV channels. What if you were to make a Yagi at the nanoscale? So the picture on the below right is a nanoscale Yagi antenna that will allow it to pick up different radio frequencies and exclude other frequencies and actually amplify the signal as if it was a Yagi antenna. You can see the separation between the bottom 2 white dots there. That's 200 nanometers. 2, 4, 6. This is 800 nanometers in length. And the dots are actually conductive. So they act like little metal radiators and reflectors. You hook a connection up to that, and you can receive radio signals at the nanoscale. Now, it's obviously directional because the Yagi is directional. But this is what they're talking about, is when they start playing around with different features, different things that they 3D print at the nanoscale level, you start to affect things. And sometimes the effects can be very useful. On the lower left, you see this sort of concentric ring-looking thing. That's actually a lens. You might have heard of Fresnel lens or Fresnel lens. That's a Fresnel lens at the nanoscale. It doesn't, because different wavelengths bend light differently, you don't have to have a completely smooth surface lens. You just need to bend different wavelengths of light so that it all comes out to a point. You can do that with certain kinds of telescopes and mirrors and lenses for focusing solar light, for creating, heating ovens and such. But that works just fine down at the nanoscale. And this one is another one that's interesting. Typically, you would not be able to focus a wavelength of light unless you had the feature of your lens be at least a wavelength of light. So if you wanted to focus 193 nanometer light down to a spot that was only 30 nanometers across, because you were making very high density integrated circuit computer chips, you've got UV light that you're using for the lithography, but you want to be able to position that UV light to less than a wavelength of UV light. By using one of these super lenses, you can actually bend the light. Even though it's 193 nanometers in wavelength, you can position it, swing it down to 30 nanometers. So they're now able to use UV light at 193 nanometers to make 30 nanometer features on integrated circuits. And they're proposing that the next step down will be smaller than 193 nanometer deep UV light, that they'll be able to steer down to single digit number of nanometers. So that's how you get even more billions of transistors on the same size chip. This one's also in your day-to-day life. Your mobile phone. How does your mobile phone know which way your phone is pointing, where you are on the earth, and can show you your Apple or Google Maps? Because they have devices in your phone that know which way your phone's pointing. Is it tilted up? Is it down? Is your phone moving along the ground at speed? What is the altitude that your phone's at? And it can do this by measuring what your phone's movement is, what your phone's tilt is and rotation is, how much the gravitational field of the earth is, how much the electromagnetic field of the earth is, so it can tell you which way north is without a moving compass needle. They do this through things called micro electromechanical systems, or MEMS devices. They have a little nanoscale finger of quartz that's sitting inside of a little area, and then they put a couple of chunks of conductive material on the nanoscale tongue that's hanging out there. And when you move the phone in some direction, or it feels the pull of gravity, that tongue deflects by nanometers. And because it has metal on it, and around the outside is more metal, it actually inducts an electrical voltage in the coil, which they can measure using very high amplitude followed by analog to digital conversion. And it can measure where your phone is, where your phone's tilted. Are you moving your phone? Where is it on the earth? It can measure all that stuff courtesy of MEMS chips, and they're in your phone today. If you went to buy a MEMS chip, the actual chip itself in volume would be about 5 cents. They can put what is known as a 10 degree of freedom MEMS subsystem in your phone for less than $1. And that will give you 3 accelerometers, 3 gyroscopes, 3 magnetometers, a pressure sensor, and a microphone. Oh, by the way, when you're talking on your phone, that's nanometamaterials, because the force of your air as you speak goes into a little hole and actually makes a little MEMS surface move up and down with the frequency of your voice and the power of your voice's amplitude. And that's how the microphone on your phone works. Nanoscale is in your everyday life today. Now, but what are they doing sort of towards the cutting edge? Here's how they're doing it. If you have a little vat, a nanoscale vat of this polymer material, and you take two different lasers and you focus the laser beam onto a spot inside the vat, at the point where the beam connects, interacts, it will make that spot get harder. Have you ever seen one of these glass crystalline sculptures where they shine a laser into a block of acrylic or glass and it makes a little tiny fracture deep inside the glass? And if you do that often enough, you can actually create a 3D pattern inside of a block of acrylic or glass. That's exactly what this is doing at the nanoscale. And because they're using a single color of laser and they're focusing the beam down to nanoscale points inside of a little vat of polymer, you get what is known as two-photon polymerization. The polymerization is you've got polymers, you've got resin, you're hardening it by inducing energy. That's called polymerization. But it's also called multiple photon lithography. The technique's been around about 20 years, but only in the last 5 years have they gone, hey, we're starting to get this good. Historically, it's been very slow because you're moving very, very small things, and you've got to make millions of little hard spots to form anything solid. It would take about an hour to create 10 cubic millimeters. Now, if you think about it, that's a hell of a lot of nanometers, but in an hour you created 10 cubic millimeters. But what if you're trying to create a microscopic lens for, I don't know, a cell phone? You can make a super lens for a cell phone in a couple of hours, which is far less time and far less effort than it takes to make them out of plastic or out of glass and then polish them by hand or put them in buffing machines. You just print the ridges on the glass to make a Fresnel lens that's a super lens. So it's like one step away from going into volume production because it saves so many back-end processing steps. But as they move other mechanisms in, you'll find that if you can make the dots small enough and you can make the density of dots small enough, you can make larger scale things that have quantum level effects. So the picture at the top, that one is from Sandia National Labs, one of the NSF's laboratories here in the US. They were just making spots, and they wanted to see how many small spots they could make on a grid. The next one down, that was from a university, and they were making larger, faster spots much closer together. Now, if you can make larger, faster spots that close together, then you get to the third image where you actually put in layers of those nanoscale spots, and you can actually make the curved surfaces and edges of the super lens. Very, very small. If you do it often enough, can make larger. Here's another example of that two-photon lithography. If you wanted to make a filter that could, say, allow certain gas molecules in and exclude others, then you just make a sieve that all the pores of the filter are small enough that only materials that have a small enough molecule will pass through your filter, and all the other molecules won't be able to fit in the holes. Now, you can do that with molecules, but molecules are smaller than photons. So to begin with, you can do that with different colors of light. You can make a filter that absolutely will not allow any blue light in or any red light in. It's just a matter of how you stack these filters. So if you're talking about making really small stuff, you can do that. But what if you wanted to make a battery? You wanted to make one of these, lithium or sodium batteries more capable of taking in a charge. If you can make the surface area of the electrode not just random waffly, but ultra smooth and have the right size pores in it to allow electrons to pass more easily without getting directed elsewhere, you could direct more electrons through that surface. And that's what they're doing. they're getting nanoscale anodes and cathodes in batteries to make it where they can have faster levels of charging and discharging. There's a company in China called CATL, and they've come up with a super lithium ion battery, and they're about to introduce that into cars in China and then elsewhere on the planet, where you can do 300 miles of charge in 5 minutes at your charging station. So if you could even do 200 miles in 10 minutes, now you have an electric vehicle that will charge just as fast as your gasoline vehicle. So we're one step away from electric vehicles with batteries where charging time is no longer an issue. And because you can pack more electrons into a smaller surface area, you now have greater charging capacity. So the next big thing in batteries for electric vehicles is nanoscale. Very, very small, very large quantities of it doing things like that. And if you can exclude certain molecules or split molecules, now you can make electrolysis where you pump water through a sieve and it breaks apart the hydrogen and oxygen without any electricity involved. So if you think about Florida Power and Light, they've got a lot of solar power and they want to convert that into hydrogen by way of electrolysis. Right now it's consuming a lot of the electricity to do that. If they use TPL-based filters to break apart the molecules with no energy, just pressure, yeah, that would make it a lot more profitable for them to make hydrogen from that extra electricity they have. So what are the three things that nanoscale 3D printing wound up having problems with? The first is accuracy. While they could make small stuff, they couldn't make high quantities of small stuff reliably. So yeah, it could do 20 nanometer, but 10% of the time it would like not be in the right place by about 20 nanometers. So you'd have spots that weren't uniform. The next thing was speed. It was going dot, 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 dot. Nowadays they can just go dots. So faster. Materials. The initial materials they used were just polymer resins. You can't make anything hard out of that. I want to make metals. I want to make stuff conductive. I want to make hard plastics. I want to make like dental crowns that will last a lifetime because they have no pores in them. Well, materials issue, accuracy issue, speeds issue. Well, in the last 5 years, they've solved a lot of that. They can now print to industrial level accuracy, smoothness. Surface defects are at the industrial scale of low now. Speed, higher millimeter cubic measurements per hour. It's still slow when you want to do really large things. You're not going to produce a nanoscale jet engine turbine blade. It'd take too long. But if you want to produce, let's say, a silicone implant that a person needs for their hearing aid or something, probably on par with being able to print that. Materials, they now have harder resins, so they can do optical parts. They have metal infused resins, so they can make things harder. They can make surgical instruments to work at the microscopic level that are extremely hard, which means if you need to make scissors for cutting very, very tiny things, you can now make them out of a material that would never need sharpening. You can make rocket thrusters, the reaction control thrusters, at the nanoscale where you don't have this problem like the Starliner has of if you leave the thruster on too long, it heats up because there's no surface defects. And you can print things that are conductive, solid state devices. Maybe you can, if it goes fast enough, do lithography. So what good is it doing this stuff at the nanoscale? Well, obviously you can steer photons by their wavelength. You can steer blood cells without accidentally causing destruction of them. You can do sampling of gases by their molecular composition without decomposing the molecules, because certain size molecules fit down certain holes, and if you have a sensor at the back end of that hole, Oh, it's methane because the methane molecule fits in that hole, but is too large for that one or too small for that one. You can do surgery or disease mitigation at the molecular level. You can implant nano robots that can find things and deal with them, unlike chemotherapy or radiation, which have a probability of hitting the wrong spot or over radiating or destroying healthy cells. But if you can send something inside the body, maybe 10 million nanobots that know exactly what your cancer looks like and can, within the next 24 hours, destroy the bulk of those cells. And when they can't find any more cells to destroy, they shut down and your body just digests them. They could be more accurate than vaccines or antibiotics. And there would be no time for bacteria to evolve or viruses to evolve because they would be completely eliminated so quickly. But on the easier side, making photovoltaic cells that produce more electricity, batteries that can charge to higher levels or that can charge faster. Here's the fun one. Take a look at that, and then I'll talk to it. This is what nanoscale 3D printer folks do in their spare time. What if I build a little nanoscale chariot that has two harnesses on it where algae will be trapped, and I have a little container and can drive around inside of a biological sample as driven by the flagellum of the algae? They just said, hey, we've got the tools. Let's see if we can do this. So they did. They built a little chariot. That's the little cube. And the two little round bullet things, those are the size of the nose of an algae cell. And the algae cells are, they get enough of them in a sample. They're just roaming everywhere randomly. And they got two algae cells to actually wind up in the harnesses. And the algae cells don't know any better. They just keep like, I need to go find some food. Let me keep rapidly flitting my flagellum. And they actually drove the chariot around in the microscope sample. Now, you can only see this in electron microscopes. So unfortunately, the algae cells were bombarded by electrons, X-rays. So they didn't live long, but now we have, think of it, we have a device, that's this chariot, that could be carrying a pharmaceutical inside the little cube that would be distributed around the body, because there's no X-rays inside the body, would be delivered around the body until the algae died, which may be days later. But in the meantime, if you have millions of these things inside you, it's delivering the medicine you need exactly where you need it. You have this chariot moving around inside your body, no motors necessary, no software, hardware needed for the driving mechanism to get it to move around. That's why they were doing the experiment is, can we do this? And once we can do this, that's how we get things to move around inside the body without having to nanoscale create motorized machines. You let the cells do the work for you. I just thought that was so cute. And there's a video link at the end where you can watch it in real time. But how does that impact astronomy? Well, when you work with nano materials that are nonlinear optics, you're making little areas that are nanoscale coated with lithium niobate, and then you apply an electrical current to that coating, you can actually change the index of refraction of the lens or the mirror. So you can steer the light electronically rather than like a mechanical focus knob adjusting the spacing between optical elements. You can electronically, with a digital to analog converter, changing the voltage in the coating, change the focus of your optical element. Now, if you can do that, think about lenses. If you have a super lens that has a nonlinear optic metamaterial coating and you apply a voltage to it, you now have a telescope where you can focus it electronically with no moving parts. With fewer parts, you have an eyepiece that doesn't need like 8 elements to bring something into high magnification. So yeah, a dramatic leap in astronomical capabilities. So right now you have things like the James Webb Space Telescope that are focusing in infrared, but there's different bands of infrared. And to go from one to the other, they actually have different instruments. So you have the near red instrument and you have the middle red instrument, but you don't have a deep red instrument. Imagine using nonlinear optics and a nano coating in your spacecraft to say, I want to be able to tune between infrared, medium infrared, and deep infrared with one instrument, one camera, one set of filters. You can now do that. So this is how nanoscale materials and 3D printing of coatings and super lenses become practical, not just for amateur astronomy, but deep space instruments. But how do we get there? Well, unfortunately, the bandwagon's got to get bigger. Once the bandwagon gets bigger for nanoscale printing, I can't predict all the things that will come about. Let's just say more quantum level effects will be controllable electronically or by making nanoscale features that steer stuff. So steering, deflecting, directing, quantum level. But will it happen overnight? No. But will it happen? There's just too much money being left on the table for it not to happen. It's just going to be done. It can't be denied. How fast? Well, once we have a breakthrough that makes something really practical for everyday users, beyond MEMS and beyond, Google Earth on your phone, once they get something that's really beneficial, and I think it's probably going to come in medical devices or in pharmaceuticals, there won't be any stopping of it. The prices will come down. The size of the instruments is already coming down. Who knows where it'll go? How small is small? So they're scaling down. They're already at the 100 nanometer level. How much smaller can it get? Well, a scanning tunneling electron microscope can currently scale down to 0.001 nanometers. That's a thousandth of a nanometer, which is actually a picometer. It's the next scale down from nanometers. But what about below that? Are we going to run into like a floor, a bottom level? Well, it turns out that IBM 11 years ago made a video by scooting around in an electron microscope individual gold and sulfur atoms. They were big enough in the right electrical conductivity that they could take a probe tip and push them around. And what they did was they made a video. They took gold atoms and pushed them around to make a dot pattern, like a pixel array, to make a picture. Once they made the picture, they got a screenshot of it. Once they had that frame of the video, they pushed all the pixels around to the next frame, kind of like a Ray Harryhausen movie, stop motion animation. They made a stop motion animation movie, and the little dots that you see are individual atoms. And they did this 11 years ago. So imagine the scale. They were down into the femto level of shoving atoms around to make a video. And at the end of the presentation, there's actually a link to the IBM research site that will show you the video. Yes, it's monochrome. Yes, it's coarse resolution, low scale. But they did it. They literally moved atoms around to make the dots 4 pixels for frames to make a video. How much lower can we actually go? Well, it turns out that once you get down to the single femtometer level, you're now down at protons and neutrons. You're below electrons. And now you have all kinds of quantum things that come into effect. Things just don't behave right. You'll put barriers up and the particle will just go through it like it wasn't even there. How can it do that through something solid? That's because it tunnels through it. You have quantum tunneling effects. So we have to come up with new things for how you deal with quantum tunneling. But there's apparently nothing in the physics that says you can't go even smaller. And the next step beyond protons and neutrons would be quarks and gluons that make up protons and neutrons. And those are about 100 zeptometers. It just keeps getting smaller and smaller. And they now have number scales already defined. I'm not making these up. The international standards community has these. You have femto, atto, zepto, yocto, ronto, and kecto. But is there anything beyond that? We got 2 more scales to go before we get to Planck limits. Or as Richard Feynman once said, there's plenty of room at the bottom.
Hmm.
How low can you go? How small can you go? Well, we've got several orders of magnitude smaller that are still available to us. We just need to counter things like quantum tunneling. Once we get past that, the ground's the limit. The ground floor is the limit, not the sky, the ground floor. So we get to conclusion, finally. So nanoscale 3D printing is currently a thing. It's not some distant future thing. They're doing it now in research and education labs. Nanoscale materials or metamaterials is already a thing and is already in consumer products. The folks that are going to be doing nanoscale 3D printing first are university, government, industrial research labs. Right now we're printing at the submicron level, but we're going to get smaller. As soon as they start seeing the Benjamins, seeing where the money is to be made for this stuff, they'll make it smaller, lighter, cheaper, faster. They just have to. Once they realize there's all kinds of quantum effects that make whatever they're doing more capable for less money, faster to produce, they'll do it. The areas that they'll first show up in are medical, cosmetics, you want that smooth, optics, you want those super lenses, machining, you want fine edges on your parts so you don't have to sharpen them again. Energy production, you want your batteries to charge charge and discharge faster, and you want them to store more than batteries. Battery storage, large scale, city storage, aerospace, you're making your jet engine turbines at the nanoscale level now. They can go faster, fly higher. Outer space, you've got rocket propulsion you can make cheaper, smaller, faster. You've got lenses that can be made from metamaterials, nonlinear optics for focusing. It's all like open, ready to do it. But you've got to get the devices trending even smaller and lower price. And first, it'll show up at the commercial service provider level. So it may cost $1 million for that nanoscale printer. But if you find a service provider who's got $10 million to invest and he's doing government contracts and he just needs some fill-in time, if you want to print something like my mythical regular pyritohedron, and you want it to be 1 meter in size, if you got a few $100s, they can crank one out for you. So yeah, it's as a service provider community, they're going to start there first to make the really high resolution stuff available at less than an arm and a leg. But they're accustomed to do that. They're accustomed to spending a lot of money to have farms of these kinds of print devices because they know there's a growing user base to do them. And as the equipment improves, the write-off time of these instruments may only be 3 years. So the amortization will be fast churn. So they'll be able to invest that kind of money again and again until they get a nice stable point where they can be doing exactly the right scale of printing and exactly the right volume and accuracy to make the Benjamins. But remember, IBM is already scooting around atoms. Once you get below atoms, you get those quantum particles deal with that. Once you've got that done, there's plenty of room at the bottom until you hit the Planck limit, which we've got several orders of magnitude away from that. So plenty of room at the bottom, plenty of industrialization room. And I did add AAVSO to my credentials list. Lots of links. Including the video about algae cells driving the nanoscale chariot. And then the IBM video of them making a video of atoms. Okay, I thought it would be fun to show how small can small get. It's got a lot smaller to go.
Unreal.
So how many people knew about the micron scale castle?
No, well.
A multiple story castle, including steps out front.
Yeah,
the tip of a
impossible.
pencil. And it's so small, the human vision cannot see it.
Crazy.
Yeah, but I think there's more, right? There you can have a lithium. I'm sorry, you can have the castle, and then you can have chariots race around it, powered by a flagellum.
Yes, but the castle is 1,000 times larger than the chariot would be. So you could have an entire army full of chariots racing around the castle.
But you know they could redo Ben-Hur.
That's true. You could see which algae cells were faster. So you got to ask yourself, why did they choose algae cells? Because if you take a sample of pond water and you want the strongest, fastest horses to pull your carriage, they examined it and said, those will do. And they picked a particular variety of green algae. And then they grew those in quantity so that when they put their chariots in the sample, some of them would find their harness and start driving around. And the video actually shows the chariot just sitting there, and then all of a sudden the chariot driving around. Now, obviously, the chariot's not going in a straight line because the two different algae are moving their flagellum at different speeds, and maybe one of the algae is a stronger swimmer than the other. So it doesn't go in a straight line. It kind of like wide corkscrews.
Am I the only one that didn't know that algae move, that they have flagella? I thought they were just
No,
kind of,
particular algae do. But there are different kinds. Some algae have cilia, so they have little hairs around the outside and they move around based upon that. Other have flagellum. And then some just sit there like cells, bumps on a log, so to speak, and float in the
yeah,
water. So
yeah.
the
That's what
ones
I
in
thought.
pond water are more likely to want to move around. The ones out in the ocean, they just let the wave action move them around. And then a giant whale comes along and gobbles them all up and consumes them.
Do you have a link to the chariot video?
Yes, yes,
Anton Petrov had it
yes,
in the last day or two.
yes. And as usual, I did my rabbit hole dive. I started with Anton because he's always got interesting stuff to look at. And then I followed, if you watch his video and then you go to the details of the video, he'll have links in there and then you can find it to his sources. Kind of like I do. If you go to the BA YouTube site and you see a video, if you look at the introduction to the video, you'll find that laundry list of hyperlinks and they're all clickable. So you don't have to hand type in that long name. You can just click. And you can't do that on the video portion itself. But if you go to the intro at the head of the video before you start it, you look at the intro, there's just a wealth of links there. And I did that on his to find out, hey, it was some guys in Japan that did this. How did they pick the algae they wanted? And how did they know it worked? And how did they see that? So rabbit hole deep dive.
That's cool.
Now, when I send the email out every week, I do send a PDF with it. The PDF is your personal copy of this presentation, including the links at the end, which are clickable because it's a PDF.
Monroe, I have a question.
Yes.
I don't know when they found all these smaller particles. I haven't, or whatever you call. I know I'm not using the right terminology, but I know about charms. But what's smaller now? You had a list
Okay.
of all the new things.
There are
But I
molecules.
haven't heard.
There are molecules, and molecules are made up of atoms. Atoms
Yes.
are made up of protons, neutrons, and electrons.
Yes.
As far as we know, unless you blow them apart, electrons aren't decomposable. But protons and neutrons can be decomposed down into quarks and gluons.
Uh-huh.
And when you
Know
decompose
this.
the protons and neutrons, you actually get multiple kinds of quarks. You get top quarks, bottom quarks, charmed quarks, strange
Yeah.
quarks, up and down quarks. So
Yes.
you get multiple kinds of quarks. Gluons,
Okay.
as far as we know, there's only one kind of gluon. But those are all, below molecular, below atomic, subatomic particles.
They may
Okay.
not be really particles either.
Well, they
They-
call them particles, but they're actually wave interference actions.
Ah. Very good, Joe.
Remember, we thought light was a wave until we got down to the quantum level at the nanometer level, and all of a sudden these waves started acting like individual particles.
Oh boy.
So photons, light, has a duality. Depending upon what you're doing, they'll act like a wave or a particle. I think they're neither a wave nor a particle. We just don't quite understand them enough, but our analogs, how we think of them are, well, when it's doing this, it's kind of like a wave. When we're doing this, it's kind of like a particle.
Uh-huh.
So particle wave duality, we just don't, it's like spin. Subatomic particles have this attribute called spin, and it can be like positive or negative, left or right-handed spin.
Yes. Yes.
It isn't the actual spinning of the particle. It's just when I blow apart a proton and I get some subatomic particles coming out of the blown apart proton, and some go this way and some go that way. Hey, they must have had different spin because they went that way and they went that way. And we know that if you have something spinning like a top, if you push it, it'll go that way or it'll go that way. So it must be spin. But spin is actually just referred to as chirality. But to make it easier for people to understand, we go, it's spin, it's left hand, right hand rule, spin. But it's not actually spin any more than they're waves or particles. It's just, this is how we understand them. Until it gets to be too silly, and then we just call them strings.
Thank you.
You're welcome.
I just don't want to miss anything that was being new on the horizon, that they broke it down to even smaller.
Well,
do they think they're going any smaller, or that they're
Yes.
not going to say this
Yes.
time?
Yes, the Large Hadron Collider over in Europe, they would like to build something that's not a whole new collider. It's just like kind of a bigger loop on one side. They'll keep the existing one, and they'll use the existing instruments, but they want to get even higher energy levels because there are things they want to break apart that they can't currently break apart.
Aren't they building that?
I don't know if they've got the billions for it yet, but
Wow.
it was down to we need the European Union to approve the billions for it.
I
But they
thought it was
already
under
have the
construction.
design for it.
Yeah, yeah.
Yeah.
Do we have anybody protesting that they're going to blow up the world yet?
That, and there's always people believing the earth is flat.
You know what I'm saying is that
Yeah,
the
I mean,
last
there
time
were
they
people
thought the
that
world was going to be blown up when they did the collider.
not blown up so much, but they kept thinking that when they go for the Higgs boson, they could create nanoscale black holes that would suck the entire earth into them.
Okay.
And
But they thought that the Earth was going to get destroyed. There's nobody
Yeah.
thinking we're going to destroy with this new thing.
yes, but remember, when they detonated the first fission atomic bomb, there was a small probable chance that they would burn the atmosphere off the earth with one
Right.
bomb.
Is that true that they did?
Yeah.
They put
Yes,
that?
oh, absolutely. It was a number greater than zero, low single-digit probability that they could have ignited the atmosphere and destroyed the earth. Now,
Wow.
did it happen? No, because it was a low probability. When they found the Higgs boson, or the indication of the Higgs boson, the Higgs field, did it destroy the earth? Did they create nanoscale black holes? If they did, it didn't destroy the earth, and if they did, they didn't detect them. So even if they did create nanoscale black holes, they lasted such a short period of time, maybe femtoseconds, that they had no time to do any effect. They say the same thing. Well, they have said the same thing about, you remember me mentioning there are different kinds of quarks?
Yes.
They've created a quark called a strange quark.
Yes. I know that one. Yes.
A strange quark is the heaviest subatomic particle they've ever measured. It's like off the scale heavy.
Yes.
But because it only lasts a fraction of a nanosecond, they go, don't worry about it. But we have strange stars. These are neutron stars where the neutron material compresses even further at the core to squeeze the neutrons apart down into their sub-neutron particles called quarks. So you can have not just neutron matter, but you can have quark matter stars. And they were predicting what kind of quark matter would it be? It would be strange quarks, because that's what the math told them. I said, well, what about going past that? If that's a progression, why not go from strange to top? Because top is so heavy and so short-lived that you're completely ignoring it. If you can have enough strange matter, enough strange quarks to make matter of it at the scale of a star, like a quasar, why can't you do the same thing with the top quarks? There's nothing mathematically that would prevent you except, well, they're so short-lived that it's just impossible for it to ever happen. Oh, impossible.
Over my head, over my head.
kind of like those black holes are igniting the Earth's atmosphere. Impossible. I like to think of it like impossible, like you're never going to be able to find elemental sulfur on Mars. Never, never, never. And guess what we just found on Mars? Elemental sulfur in quantity. Huh. Fancy that. Whenever a simulation, a computer simulation or a mathematical model says, never, ever, ever, take it with a grain of salt. And depending upon what's going on, a small grain, a nanoscale grain of salt, or a large grain of salt, like, you're kidding, right? Okay. Any other comments or questions before I stop recording? Hearing nothing.
It's a good topic. I like it.
I liked it too.
Thank you.
What will I do next week? You shall see.